Okay, we're going to focus today on inequalities and inequality proofs. The reason we're doing this is because in induction, quite a few problems are stated in terms of inequalities. What I want to do is, rather than assuming that you know all of these different properties of inequalities, we're going to focus on these, make them explicit so they can be used in the induction proofs. To start off, I want to go through some of the introductory definitions, axioms, and theorems. As we have talked about in our class, axioms are items that are assumed to be true. So I have 4 axioms. One I've added recently, which is called the positivity axiom, which basically states that for all real numbers, exactly one of the following is true. Either x is positive, written x is greater than 0, x is negative, written x is less than 0, or x is equal to 0. So one of those 3 is true. Exactly one. And then axioms 2, 3, and 4 focus on operations with positive and negative numbers. If you have a number that is non-negative, so greater than or equal to 0 is non-negative is what it's called. And let me back up. And there we go. And b is also non-negative, then a plus b. If you add 2 non-negative numbers, you get a non-negative number. A times b, so if a is positive and b is positive, a times b is positive. And then lastly, if you take a positive and a negative and multiply them, you get a negative. Okay, with these axioms, again, axioms are things that are assumed to be true. We can talk about some definitions. What does it mean for one number to be less than or equal to another number? All right, so this is definition 1. Definition 1 states that if a is less than or equal to b, or excuse me, a is less than or equal to b if and only if, and remember, if and only if essentially means it's bidirectional. If and only if there exists a positive, or non-negative rather, k, such that a plus k equals b. A is strictly less than b if there exists a k that is strictly positive. Okay, such that a plus k is equal to b, assuming is equal to b. So essentially what this is saying is that a is less than b, so a and b on a number line. Here we got a and b. A is less than b if there is less than or equal to, if there is some positive distance, which we'll call k, that you have to add to a to get up to b. You can also talk about these definitions in terms of greater than or equal to, and I've listed them here. What I'm going to do, in general what a lot of people do, is it's good to know both of these. I mean, so that you can sort of switch back and forth between positive and negative. I'm going to try to be consistent and basically try to express everything in terms of less than. It's just a simple then transformation if you want to then talk about things in terms of greater than. But I figure let's make sure we work carefully with just one of these and get competent, get really good with one of those, and then we can move on to the other one if we wanted to. Okay, so once we have these axioms, these definitions established, then you can talk about some common theorems. Theorems are truths, statements that are derived from the axioms and definitions, and there are 8 that are commonly come up. These are not the only 8 that exist, but these are 8 that are commonly used in induction proofs. Okay, and a couple of them are pretty standard, basically what you consider or kind of extensions of what you do in algebra. The additive property of inequality essentially says that you can add some item to each side, some real number to each side. And note that that real number doesn't need to be necessarily positive or negative, it's just any real number. In these theorems, A's, B's, and C's are only positive. Okay, and the only reason I did that is not that we can't have inequality axioms or theorems for negative numbers as well, but induction often, most induction problems, especially in an introductory course, focus on essentially positive sequences. N is 1, N is 2. So generally you're dealing with just positive numbers. The multiplicative property of equality states that you can multiply both sides of an inequality by a positive number, and the inequality remains the same. Transitive property: if A is less than or equal to B and B is less than or equal to C, then A is less than or equal to C. And then we have some other useful ones. 2 says essentially, and this is a very useful one in induction, if A plus B is less than or equal to C, now notice all of these are positive, then that says that each part, A is less than or equal to C, and B is less than or equal to C. So both of them. So think about it in terms of, just simple addition. 2 plus 5 is less than or equal to 8. And with all of these being positive, what does that imply? That implies that 2 is less than or equal to 8, and 5 is less than or equal to 8. So in other words, from these you can get two truths that both pieces are less than or equal to 8. Now what you'll find in induction, as you'll see, is from this statement, 2 plus 5 is less than or equal to 8, I could say that implies 2 is less than or equal to 8. And I have many students who'll say, well, what happened to the 5? Well, it's because of this induction. Each piece, not induction, this theorem rather, each piece is less than or equal to 8. So the other theorems you should know, and these are things that we'll use, just have these available to you. You are welcome to use these in you don't need to memorize them. They're things that you can use in class. You can have a copy of these on your tests, and if we had quizzes. But I want you to be able to use them. So what we're going to do first of all is just use these in a theorem. Okay. We're going to prove one of the theorems. Again, what's what I mean by prove? We're going to derive this theorem from basically from our axioms and definitions. And it says the first one of, and this is, which one is this? This is A plus B and X is less than. So which one is that? That one looks like theorem 7. Okay, so theorem 7. Okay, so we want to prove using our axioms and definitions that if A plus B is less than or equal to C and X is less than or equal to B, then A plus X is less than or equal to C. In other words, if I substitute something smaller, if this statement's true, oh, there you go, let me get my pen back. Come back, old pen. And there we go. If I substitute something smaller into the expression, so A plus B is less than or equal to C, and I substitute something smaller. There we go. Fumbling with my pen, as you can probably tell. So if A plus B is less than or equal to C, and I put something smaller in that space, that expression is still going to be less than or equal to C. So what you often want to do in a general strategy for these proofs is to convert these statements from inequalities to equalities and use that we've established, what we know from algebra. So we know that as a conditional statement, if P then Q, we want to assume the hypothesis. So let's assume that A plus B is less than or equal to C and A is less than or equal to B. And in giving that assumption, note that A's, B's, and C's are positive real numbers, and X is just any real number. All right. Now, once you've made that assumption, we want to translate those into equalities. So what you can say is that basically from the first one, so using the definition of less than from our definitions, we know that since A plus B is less than or equal to C, that there exists some epsilon 1 such that A plus B plus epsilon 1 equals C. I should have written that all on one line. And since X is less than or equal to B, there exists some epsilon 2 such that X plus epsilon 2 is equal to B. And notice that those, by the definition, are non-negative, so greater than or equal to 0. All right. So now what we can do is we have algebra at our disposal, if you will. We can substitute, take the X plus epsilon 2 equals B and substitute that into your first equation, and that gives you A plus X plus epsilon 1 equals C. Okay? Now, we have to say, well, what do we know about our epsilon 1 and epsilon 2? Epsilon 1 and epsilon 2 are both positive, non-negative rather. So that says, and this is where the axioms come in, since epsilon 1 is greater than or equal to 0 and epsilon 2 is greater than or equal to 0, then some new epsilon, which I'll call epsilon 3, which equals epsilon 1 plus epsilon 2, is also greater than or equal to 0. In other words, if you take two non-negative numbers and add them, you get another non-negative number. Now, my strategy for doing that is I want to substitute this for my epsilon 3. Okay, and that is by axiom 2, this statement. All right, so what does that say? That says that, and let me go back and write that up there, that says that there exists some, remember what we did is we substituted. We put epsilon 3 right there, epsilon 3. So there exists some non-negative epsilon 3, which is greater or equal to 0, such that a plus x plus epsilon 3 equals c. And that says, by the definition of less than, that's our definition, that there's some positive numbers such that a plus x equals c. So by the definition of less than, we know that a plus x is less than or equal to c. So anyways, each of the theorems in each of the inequality theorems can be derived like this from the axioms and definitions. I encourage you to get a little practice with that. May show up on a test or quiz at some point. But anyways, these are the most important part. And let me go back to that screen. The most important part is that you know these inequality theorems, and that you get used to using them, which we're going to do in induction inequality proofs.